Okay, I've first of all constructed a forpling graph, and I'm going to construct a series of trapezoids for the forpling graph. So what I'm going to do is I'm simply going to connect this point to this one, and then this one to this one, and then this one to this one, using approximating segments to create 1, 2, 3 trapezoids. So I'm going to do that mostly off camera, but let me do just a little bit of it on camera here. I'm going to construct the approximating segments. And I notice that the approximating segments here stay pretty close to the graph, but the graph, having an upward concavity, really goes a little bit below the approximating segments. Now, if I can do a decent approximating segment here, it'll be clear how the graph dips down below the segment. Now, that's not particularly well drawn. I ended up a little high on that point, but we're going to live with that. Now, let me add a little bit more to the graph. Okay, I've added my projection lines. Now, I can't label these trapezoids because this graph is unlabeled. But I want to compare the slopes, compare this slope to this slope to this slope. And you might want to think about how to do that. I'm going to draw a little bit more here. I'm going to draw the triangles we use to calculate the slopes. You might consider doing the same thing. Okay, now you should be able to see the dotted lines I've used to construct the triangles. This one's probably easiest to see. Dotted line goes up to here, across from here. One side of that triangle, one leg of that triangle, is going to represent the rise. Another leg, the other leg, is going to represent the run. Similarly here, we have a rise, we have a run. And down here, the dotted line I would use from here to here would have been inside the y-axis. But here's the rise, and here's the run. Now, see if you can determine what the ratio of the slope of this triangle, what's the ratio of this slope to this slope, what's the ratio of this slope to this slope, and what's the ratio of this slope to this slope. Should be fairly easy to make those determinations, assuming this is a good forpling graph. Now, if, as a hint, we could start with, let's say this is trapezoid 2, trapezoid 1, trapezoid 2, trapezoid 3. So rise 2, that is the rise of the second trapezoid, is what multiple of the rise of the first trapezoid. What number would you put in here? And then how would rise 3 correspond to rise 1? How many times this rise is this rise? Further hint, from here to here, the y-coordinate forples. That gives you enough information to compare the rise of this triangle with the rise of this triangle. Bigger hint if you need it, the forpling implies that this is 4 times this. So what does that tell you about how the rise of the second trapezoid corresponds to the rise of the first? Okay, it should be clear that this is the rise of the first trapezoid, and this is the rise of the second. At least this arrow is equal to the length of that rise. This arrow is equal to the length of that rise. Meaning that if this is 4 times as big as this, then this minus this is equal to this, so it's only 3 times as big. So that the rise of the second triangle is how many times the rise of the first? Well, I've replaced it, the question mark, by the correct number. The second trapezoid has a rise of 3 times, that is equal to 3 times the first. Now, how about we compare the rise of the third trapezoid, which is of course wider, with the rise of the first? How many times the rise of the first is the rise of the third? Okay, so we can note then that rise 3, the rise of this trapezoid, well, it goes from 4 times as high as the first up to 16 times as high as the first, which means that it's going to be 12 times the rise of the first, because from 4 to 16 is 12. So from here to here is 12 times the rise of the first. So rise 3 is 12 times rise 1. So what do we conclude about the relative slopes of these three trapezoids? Slope of trapezoid 2 is how many times the slope of trapezoid 1, and slope of trapezoid 3 is how many times the slope of trapezoid 1. Let's reference everything back to the slope of trapezoid 1. You should think about that. Okay, so hopefully you've stopped and thought about that. Trapezoid 2 has the same width as trapezoid 1 and has a rise that's 3 times that of trapezoid 1. So if when we do rise divided by run, we're going to divide this rise by a run here, and we're going to divide this rise by the same run. Since the run is the same in both cases, and this one has 3 times the rise of this one, then the rise here is going to be 3 times, or the slope is going to be 3 times that of trapezoid 1. Slope of trapezoid 2 has to be 3 times the slope of trapezoid 1. Now, what about the slope of trapezoid 3? Again, you should figure this out before you see my analysis. But now I'm going to proceed. Okay? The rise of the third trapezoid is 12 times the rise of the first. So you'd be excused, if you were tempted at least, to write 12 here, because since we had 3 times the rise here, we got 3 times the slope. So now that we got 12 times the rise, we should have 12 times the slope. But there's something wrong with that. And if you thought that, can you think through what's wrong with that? Okay, again, hopefully you've done that. What's wrong with that is we also have twice the run. So let's see, we've got 12 times the rise, but twice the run. Okay, so that gives us what? It gives us 6 times the slope. Now I'm going to write down a couple of things. Okay, so the reasoning is 3 times the rise divided by the same run is going to give you 3 times the result. We're dividing rise by run. If the rise is 3 times as big and the run is the same, that means the quotient is going to be 3 times as great. However, if you got 12 times the rise and twice the run, then you're dividing a number that's 12 times as big as it was for the first trapezoid by a number that's twice as big. If you divide a number that's 12 times as big as another by a number that's twice as big, and syntax in that statement isn't great, but if you're dividing 12 times the rise by double the run, then you're going to get 12 halves, 12 over 2, or 6 times as great as the slope. So the slope is 12/6, or 6 times as great. Put parentheses around that so we know what's equal to what. Now, the distance from the origin to the middle of the second trapezoid, that would be this distance, is how many times, to the second trapezoid would be this distance, is how many times the distance from the origin to the middle of the first. Then, distance from the origin to the middle of the third trapezoid is how many times the distance from the origin to the middle of the first. Think about that. See if you can come up with answers before you view my response. Well, this distance is double this distance, and this is half of that distance. Now, this distance has to be equal to this distance, since this distance is half of this distance, which is equal to this distance, so that this has to be a half, and a half, 3 times as great as this distance. We didn't have to do any algebra, we didn't have to use any formulas. We could do this with a compass and a straight edge. Bisect this segment, you get this one. Set the compass down here, set it down again, set it down again, you get this. Geometric thinking, very important and underutilized. And we want to be able to think geometrically. One of the purposes of this exercise here. Okay, well, what about this? Well, this distance here is half of this distance. This distance is double this. so that this distance has to equal this distance. Now, this distance is 2 times this distance. This distance being equal to this distance is 2 times this distance. So we have 2, 4, 6 times this distance. Again, these intervals are all equal. So we got 1, 2, 3 of these intervals out to here. Each of these intervals is twice as big as this one, so that this is 6 times this distance. So we would write down our results: 3 times the distance and 6 times the distance. Now, do we see any pattern in any of our results here? You should look at your results and see if you see a pattern. Well, hopefully you do, but I'm going to go ahead and circle it. The slope and the midpoint of each trapezoid are in the same ratio. That is, the slope and the distance from the origin to the midpoint, or if you wish, the slope and the coordinate of the midpoint of the trapezoid are always in the same ratio, and that ratio, in terms of the dimensions of the first trapezoid, or the quantities we get for the first trapezoid, those ratios those numbers are identical. Okay, this midpoint is 3 times as far as this one from the origin, and this trapezoid has 3 times the slope of this one. This one has a midpoint that's 6 times as far as this one, and its slope is 6 times as big as the first. So now, what does a graph of slope versus midpoint of a trapezoid look like if you have a forpling graph? What do you think that graph is going to have to look like? Okay, just as a hint in case you don't see it completely, if this coordinate here corresponds to the position of the midpoint of the first trapezoid, and this coordinate on this axis corresponds to the slope of the first trapezoid. Now, we don't know what the slope is, and we don't know what the coordinate of the midpoint is, because this graph is completely unlabeled. We just know these things as multiples of quantities that relate to the first trapezoid. So what is our result here? What is this graph going to look like? Well, you should think about that a little more, but I'm going to go ahead and do it. We know then that this point is a point on the graph, and that if we go out 2 more midpoint distances, we're going to be at 3 midpoint distances, and the slope is going to have to be 3 times as great as the slope was here, which is going to give us a point, if we project over and down, right about here. And then if we go out to 6, which is just me moving a couple of times the triple distance, okay, we could get a point here and here. In other words, 6 times the midpoint of the first, 6 times the coordinate of the midpoint of the first would be about here. 6 times the slope of the first might be up about here. And that would give us a point over here and down here, somewhere up about here. Now, what do you think those 3 points indicate? And I kind of made that one a little too far to the left. I tend to do that. Should be over closer to here. Okay, well, since all these units are the same and all these units are the same, it's pretty clear that this graph is going to have to be a straight line through the origin. Now, does this straight line through the origin, which could be extended as far as we like, does this graph actually apply to other trapezoids that we could construct? We could construct a trapezoid based on any 2 points on this graph. Would it work for every possible trapezoid? If this trapezoid is at distance 5 from the origin, 5 times this distance, does it have 5 times the slope of the first? Of course, referring to the distance at the midpoint and assuming a perfectly drawn forpling graph. Can we prove that would or would not apply to any graph drawn anywhere on a perfectly drawn forpling graph?